Hey guys, so we are now to the third video for chapter 15, which is going to be all about inferential statistics. So we're going to be talking about learning objectives 7, 8, and 9 from your chapter. So we're going to identify the general purpose of hypothesis tests and how those tests accomplish the goals of the researcher. We're going to define type 1 and type 2 errors and why they occur and talk about the consequences of each of those. We're going to talk about how sample size and sample variance influence the outcome of hypothesis tests and why we need to measure the effect size to as like a supplement. Okay, so remember, research typically uses samples, right? And we use that like as an estimation of the population. But the potential problem with that, or well, not potential, it is a problem with that, is that um, we have questions like, does this sample accurately represent the population? Can we rely on that? And if we, or along the same lines, if we selected a different sample, would we get different results? And so can we really trust these results? And so inferential statistics is going to be what helps us answer those questions and concerns. So remember, the basic goal um, is to use the limited information from samples as the basis for reaching those general conclusions about the population. Um, so again, it's addressing the issue of how accurately that sample is representing the population. The basic difficulty with this is sampling error. And so, what is sampling error? Well, it's the natural difference that happens between a sample statistic and the population parameter. Basically, there's always going to be a discrepancy, right? The sample is not ever going to perfectly represent the population, no matter how um, much you go through in your research process and your sampling process, your research design, everything. There's still going to be differences, right? It is not the same thing as the entire population. So there's always going to be a little bit of sampling error. The question is how much. To give you an example of sampling error, there's figure 15.8 in your book, but we have the parameters right here um, in on these next two slides. So the population parameters, you see average age is 21.3 years, average IQ is 112.5, and then 56% female, 44% male. So this is the population parameters, right? So we select two different samples. So sample one is these 5 students, and we find that their average age is lower because remember the population was 21.3. The IQ is lower because the population IQ was 112, and the male-female breakdown is different because there was 56% female and 44% male in our population. So the sample does not completely 100% accurately represent our population, right? Well, then we select a different sample. Again, average age is a little bit lower. It's closer to the population. The population was 21.3, but it's still lower and it's still different than the other sample. Our population IQ, again, remember, was 112.5. So this one's actually higher. This sample actually had a higher IQ average than the population. And then again, female male breakdown is way different because the population is 56% female and 44% male. So the idea here is for you to notice that the sample statistics are different from one sample to another and definitely different than the population parameters. And so there's always going to be that sampling error. The fundamental problem for inferential statistics is to differentiate between results that represent real patterns and real relationships, real results, real effects, and those that are just because of sampling error. So you get these results and you have to determine, is this real? Is there really something going on with these variables? Or is this just a result of sampling error or chance, so to speak? And so that's the fundamental problem, issue, whatever, with inferential statistics and what inferential statistics tries to solve. 15.9 in your figure 15.9 in your book talks about this. So this is examining the difference between television violence and aggressive behavior for preschool children. So you've got your circle population of preschool children. You've got two samples, again, just like we did with this other sampling error example. You've got two samples here, but here we're comparing treatments. So we've got one, the sample one is assigned to the nonviolent TV treatment or condition, and then sample two is assigned to the violent TV condition. And after that, their means are assessed for aggression, and the average mean for sample one is 3.4. The average mean for sample two is 7.6. You see that at the very bottom there. And so there's a 4-point difference about between the sample means. So does that mean that watching violence on TV actually did increase the aggression in sample two? Like, is that 4-point difference real? Does that mean that the treatment, the violent TV watching, had an effect? Does it mean that those two samples are significantly different from each other, or is it just due to chance? Or sampling error? Just like you saw those two samples that we selected in the slides before, in these slides, those two samples were very different from each other, but that was just by chance. That had nothing to do with the treatment, right? So how do we separate what is sampling error and what is due to the treatment? Well, that is where hypothesis tests come in. And so what is a hypothesis test? It's a systematic procedure that is determining whether the sample data is convincing enough, has enough convincing evidence to support your research hypothesis, which again is about the population, right? Your hypothesis is always going to be about the population, because you're not just concerned about that particular sample. You're always going to be concerned about the population that you drew your sample from, right? And so the hypothesis test, in essence, is trying to see if we have, again, enough evidence to support our hypothesis that the population, or that our results in our sample, could also be applied to our population. It's also a way of testing the internal validity of a research study. The hypothesis test, it ensures that internal validity, because you remember, our internal validity is that there's no other alternative explanations for the research. For your results, and that's what you want, right? You want there to be, the only explanation is the difference is real, that the treatment had an effect, or whatever your study is. Being due to sampling error or being due to chance is another explanation, right? And so if your hypothesis test is showing that it's not due to chance and that there is a real effect here, then that is ensuring the internal validity of your study, because it's saying there's no other alternative explanations, including chance. So the goal of the hypothesis test is to rule out chance as a plausible explanation for the results. So there's 5 basic elements for the hypothesis test. And the first is the null hypothesis. The reason it's called null is because it's always predicting nothing. It's predicting that there's no effect, or no change, or no difference between groups, or no relationship if you're looking at correlations. It is predicting that nothing is going to happen as a result of whatever you're studying. And so it's a statement about population, obviously. But it's what your sample is trying to combat. I hate to say combat, but because you don't want the null hypothesis to be true, right? You want to show that there is an effect. That's the goal of your study. Your research hypothesis that we talked about developing way back in chapter 2 or 3, we talked about it needed to be a positive statement because we want something to happen, right? We want there to be a difference. We want to show there's a relationship. Um, and so the null hypothesis is the exact opposite of your research hypothesis. Okay. Um, it is basically what the population parameters should be if nothing happened, if there's no relationship, no effect, no change. It is the hypothesis test is basically determining if there's enough evidence to reject this null hypothesis and conclude that yes, there is a difference. Our research hypothesis was correct. So that's the null hypothesis. A sample statistic is, let's go to this second point down here. This is whatever you're using. If you're looking at correlations, then your null hypothesis would be predicting that the correlation would be 0 in the study, and your sample statistic would be the correlation that you are obtaining in the study, like what you're calculating. The sample statistic is what you're calculating. It's what you're comparing to the null hypothesis to see if there really truly is a difference. And again, it says if the null hypothesis states that there's no difference between two population means, then the sample statistic would be the difference between the two sample means. So the standard error is the average size of the sampling error. So this is basically a numerical way to show what the sampling error is. It's the average difference between the sample statistic, and the parameter. It's basically telling you how much discrepancy to expect. We talked about sampling error is that discrepancy, the difference between your sample and your population. This is telling you how much discrepancy to expect. Um, and so, but like I said, it's a calculated value. And so that is the standard error. And again, that's very helpful information to know how much discrepancy to expect, just based on chance, because we want to know if our difference is due to that or if it's due to something else. Then your I can't talk. Your test statistic is what you're actually using as your hypothesis test, what you're using to determine the difference, or the whether there's an effect or whatever the case may be. And so that is the mathematical technique that you're going to use to compare the sample statistic, like I said, with the null hypothesis. You're going to compare your sample statistic with your null hypothesis, and you're using the standard error as the baseline, again, because standard error is telling you how much is due to chance, how much discrepancy you can expect based on chance. And so you're saying, I want to compare to that and see if ours is more, if our sample statistic is more, and so then we can reject that null hypothesis and say there was a difference. On here, it shows you like in a calculated way, sort of. Of course, there's lots of different test statistics. We've talked about a lot of them, t-test and ANOVA, and we've talked about lots of different ones, but this is the basic structure of all of those tests. What they're doing is looking to see if your actual difference, you see this bottom one, it says actual difference is the actual difference between the data and the hypothesis, or your sample statistic and your null hypothesis. You can see that up at the top. Is that greater, because it's on the top of the division equation, is that greater than the difference that is expected by chance, or the standard error, as you see in the equation above? So that's what the test statistic is telling you, is whether or not those are, it's bigger, your difference is bigger. So if you think about this conceptually, if they are close to the same, if the difference between the groups, or whatever it is you're testing, if the difference between your null hypothesis and your actual difference, your actual sample statistic, if it is bigger than what would be by chance, by if it's bigger than that standard error, then your number would be a lot bigger than 1. But if it's close, if they're close to the same, if it's basically by chance, it's going to be near 1, because those two numbers, the top and bottom numbers, are going to be close to the same, which means when you divide them, they're going to be close to 1, right? Because a number divided by itself is 1. And so we want that test statistic usually to be a lot larger than 1, so that we can say that that means that our results were not due to chance. I think that's, yeah, okay, that's all I wanted to show you guys there. Just so you could see that conceptually. Okay, and then the last element of a hypothesis test is alpha level, or what we call level of significance. Usually that is set to either, this is something you set for your experiment, and it is, or your study, and it is usually 0.05, 0.01. Sometimes researchers even do 0.001. Those are pretty much the three standard, but there are others. But 0.05 is usually the biggest it will ever go. Because what that is saying is that you are willing to risk a 5% chance that your results that you obtained were due to chance. So, you know, we get that test statistic and we say, okay, it's bigger than 1. Great. It's greater than chance. So our results were greater than would be obtained by chance. But researchers want to know if it's significantly greater than chance. Like if it is actually, there needs to be some sort of standard, for significance, and that's where the alpha level comes in. That 0.05 value is defining what is extremely unlikely. So our results are extremely unlikely to be due to chance, is how you would want to say it. Okay, so how do we report this? What does this look like? So remember, the goal is to establish that the results from the research study are very unlikely to have occurred by chance. That very unlikely part, as I just mentioned, is defined by the alpha level. And so it is set at a certain percentage, 0.05, 0.01. Those alpha levels, those 0.05, 0.01, that's called a p-value, is what that's called. So you'll see in research reports that p is less than 0.05. You'll see that written. What that means is that was what their alpha level was set at, but it also means that the significance, or the tests, that they ran, that the probability of that result being caused by chance is less than 5%. So we can say it's significant, right? We can trust it, because there's a 95% chance or more that our results occurred, that they were real, that they were not by chance. Okay. So you would say it's a significant result, or a statistically significant result, is what you'll see in research literature. Or if it's not, then you would see them say it's not significant. So if the p-value was 0.028, which is less than 0.05, then you would see that that notation p is less than 0.05. You would see that, or you would even see them report p equals 0.028, and they would say this is a significant result, because the chances were less than 5% that it was due to chance. Or if they actually report the p-value of that actual hypothesis test as 0.028, you could say there's a 2.8% chance that it was due to chance. Well, that's super low. So obviously, that is considered significant. Now, if it was 0.067 or 0.8 or something like that, that's higher than 0.05. So it would be reported as, you would switch that greater than, less than sign around, and it would be p is greater than 0.05 instead. And that would mean a non-significant result. That would mean that your results, there was not a less than 5% chance, there was a greater than 5% chance that it was due to chance. And so it would not be considered a statistically significant result. Now, because of the nature of this, and because of, like we said, the sample is not always exactly the same as the population, and all the other things that humans are involved here, human error. There's going to be errors in hypothesis testing, and there's two basic ones where where the misleading information that you get from your sample for whatever reason, whatever reason it's misleading, leads to that incorrect conclusion. So type 1 and type 2 are the two types here. Type 1 error is when the researcher says, I found evidence for a significant result, but there actually wasn't. So your sample was unusual or extreme, and so it made it look like there was an effect happening or made it look like there was a relationship there when it was not in the population. It's not like the population. And so there really truly isn't a effect or relationship happening there. And so it's basically a false report or a false alarm, is what the consequence of a type 1 error is. The reason it's called a false report or a false alarm is because you're saying there's an effect here or there's a relationship here when there isn't, and which is bad, right? I mean, that's, you don't want that to happen. But the good news is that p-value that we just talked about identifies the probability of this type 1 error, because, or so you can say there is a 0.05 or 5% chance of a type 1 error, because that's exactly what that is you're saying there's an effect when there's not, when it's actually just due to chance. What you found was actually just due to chance. Now, type 2 error is the complete opposite of that. So it's showing the sample data did not show evidence of an effect, but there really actually is a significant effect in the population. You just didn't detect it. So this is often called a fail to detect, because you did not detect the effect or the relationship that actually does truly exist. And most of the time, this occurs when the effect is really small, so it doesn't show up in the sample, either because the effect is just really small or because your sample size is small. And so a lot of times, what researchers will do in situations like this, when they don't obtain an effect, they worry that they're falling victim to a type 2 error. So a lot of times they will repeat the study or the experiment with a larger sample or a stronger version of the treatment or something else that's going to make it more likely that they're going to be able to detect an effect if there really is one there, so that that type 2 error doesn't happen. Now, we just kind of talked about this. I kind of segued into this. There are factors that influence the outcome of the hypothesis test, and sample size is one of them. So the number of the scores in the sample can affect it. So a mean difference, or a correlation, whatever your test statistic is, that's found with a really large sample is more likely to be significant than that same result or that same statistic with a small sample. I could get into the calculations of why that is, but just know that increasing the size of your sample increases the likelihood of detecting an effect if it's there. Okay. And so that's why a lot of times people will use larger samples than probably what you think they need to really use. And that's why using samples of like 4 people or something like that is usually not recommended. Okay, and then the other thing that can influence the outcome of a hypothesis test is the size of the variance. So how much the scores vary. Are they all clustered around each other tightly, or are they all over the place? A sample mean with high variance is less likely to be significant than one with low variance. We talked about this in chapter 8 a little bit, about that background noise, that static that makes it hard for you to see the true. Let me skip over here. That make it harder for you to see the real difference. And so the 15.10 here is showing you this is actually a duplication of the 2 figures from chapter 8 where we talked about this, and you can see that in the scenario A up here, the sample means are very clustered around each other. There's not a lot of variance. And so you can easily see the difference between the treatment condition in blue and the control condition in red. That effect is easy to see. Now, in B, the effect is the same. So the statistics did not change as far as that goes. The only thing that changed was the variance, the scores. So the sample mean, the scores within each condition are a lot more varied in this scenario on the bottom here. And you can see now that difference, gosh, I couldn't think of the word, between the control condition and the treatment condition is a whole lot harder to see visually here when it's varied, when those scores are all over the place, right? So you can see like the scores vary on this x-axis down here between 20 and 66 on B, but up here on A, it's only from 38 to 52. So you can see the scores are just varying a lot more, and that variability makes it harder to determine if there's really an effect happening, if there's really a difference, because there's so much difference between the scores themselves just in general. And so this down here was talking about how a t-test is what will be used for this particular scenario, and that the p is less than 0.001 would mean that the difference, it's unlikely that the mean difference occurred by chance in part A. But in B, because there's a large variance, that test would show no significant difference because it's so varied, even though the difference between the treatment and control is the same, but because there's so much more variance in the scores, the probability ends up being 0.084, which is a lot higher than 0.001 or 0.05 or whatever it is they set it at. And so it would look like the results were just due to chance, even though they weren't. And so having a smaller variance also can help your hypothesis test process. So if you have scores that are varied and all over the place, that can be problematic and just be something to be aware of as you go through your hypothesis testing process. Okay, so you can also supplement hypothesis tests with measures of effect size, or the size of the effects. And so those are the three ways that you can do that. Cohen's d, which we've talked about before, is primarily used when comparing two treatment means. That's usually the scenario when that is used. And basically what it is an absolute size of the effect that's not influenced by outside factors like sample size, for example. So you don't have to worry about how large or small your sample size. It takes that out of the equation, and you can actually see the size of the effect. Because here's the thing. So when you get a significant result, you get a statistically significant result. That's great. That's good information to know. But a lot of researchers want to take that a step further and say, okay, there could have been a lot of other factors that influenced that statistically significant result. I want to know how big this result is, how big this difference is. What's the size of this effect? So it has an effect, a significant effect, great. But what's the size of the effect? How much influence does this variable have on this variable? Or how strong is this relationship between these two variables? And so that is where these three things come in, especially Cohen's d. Now I'll show you what this looks like. So Cohen's d, there's the basic idea there. It's the sample mean difference divided by the sample standard deviation. And that basically is telling you, it says, if you got 2, that would mean that the mean difference is twice as big as the standard deviation. And so it shows you a little graph here of what that looks like. So that would mean that, the down here at the bottom, when there's 2 standard deviations, the part B down here at the bottom, that's obviously those are 2 very different distributions of scores. So there is definitely a difference happening between the 2 sample means, right? You can see that clearly with the two curves there. Table 15.3 here shows you the criteria for evaluating an effect size. So if you get, 0.2, then that's a small effect. If you get 0.5, that's a medium effect. If you get 0.8, that's a large effect. So that kind of gives you an idea of how when to say this is a small effect size or a large effect size. And examples of how to calculate Cohen's d and the other two things we're going to talk about, remember, are in Appendix B, just to remind you. Now, there's also the percentage of variance accounted for. That's another way to do this, and we talked a little bit about this before as well. R squared, or eta squared, is what that Greek symbol is. Basically, this is allowing you to, it's telling you the percentage of the variability in the scores in one variable that's accounted for by the other variable. And so it's giving you somewhat of a predictive ability. When we talked about this with regression and that line, it's enabling you to predict what the scores will be on one variable when you know the score of another variable, or when you know the sample score, you can predict the population score to a certain extent. And so table 15.4 here is showing you the criteria for how again, how you can evaluate the effect size there. And that kind of tells you here, 0.01 means 1% of the variability can be accounted for, or medium effect is 9%, large effect is 25% or more. Okay, and then confidence intervals is the third. You see that? Okay, we're going to go back. And so the confidence interval is basically, again, to help estimate those population values, which I kind of alluded to just a second ago. If you know the sample, you can predict the population, and it's an interval. So like if your sample mean is 60, it tells you here, calculating the confidence interval would tell you the range that what you can add to and subtract from the mean to give you a range of values where you can say we're confident that the population mean will lie somewhere between 55 and 65, or between 30 and 90, or 50 and 70, or whatever that confidence interval ends up being. The problem with confidence interval is that it is influenced by sample size. So just like hypothesis tests, percentage of variance and Cohen's d is not. So those are more reliable most of the time ways of calculating an effect size. Confidence interval can be good if you want to know what the range is of values for the population, but you have to keep in mind that that is influenced by sample size. Okay. We made it through. Woo! All right. So the learning check for this, when a sample is selected from a population, the sample mean essentially is guaranteed to be different from the population mean. We talked about that. It's not going to be the same. What is the name for the naturally occurring difference between that sample statistic and the population parameter? And hopefully you guys remember that is called the sampling error. That was the first thing we talked about in this video. If you don't remember that already and you're thinking, what? Then rewind this and go back and watch that again, or go back and read that section in your textbook. And then a researcher reports a significant correlation using an alpha level of 0.01. Which of the following is the accurate conclusion from that result? So if it's 0.01, then that means that if you look at these answers, it's talking about type 2 or type 1 error. Well, the alpha level doesn't have anything to do with type 2 error, remember? So that rules out the bottom two. So it is actually that the probability that the researcher is making a type 1 error is less than 0.01, okay? Remember, the type 1 error rate, if you want to call it a rate, is the same as that p-value of 0.01. So the probability that the researcher is going to make that type 1 error that's going to say that there was an effect when there was not, so they're going to say there's an effect when it actually occurred by chance, is 0.01. or a 1% chance. Okay, and then the last one is what is measured by values such as Cohen's d or r squared, which is the percentage of variance accounted for, which we just talked about that. That is effect size, or they have it here as the size of a treatment effect or the strength of a correlation. Because again, it is called effect size because a lot of times it is used for effects of, between conditions or of a treatment or of a manipulation, but it can also be the strength of a correlation. That's the same idea. Is how big is this effect? How strong is this relationship? That is that. So if you guys have any questions about 15.3 or about chapter 15 in general, just email me.